The solenoid in this problem consists of 600 turns, and it has an overall length of 15 centimeters. We can calculate the number of turns per unit length then as little n, and it works out to 4,000 turns per meter. The magnetic field magnitude at the center of a long solenoid equals mu naught times little n times the current I. When you substitute values and calculate, you find that equals 0.0402 Tesla. So that's the answer to the problem, but the more interesting thing is to see where this expression mu naught Ni comes from. We can obtain that using Ampere's law, which tells us that the line integral of the magnetic field around a closed loop equals mu naught times the current enclosed by that loop. If we return to the solenoid in the drawing, we can argue from symmetry that the magnetic field inside the solenoid should be parallel to its axis. I'll draw it this way, and the magnetic field outside should be approximately zero. With the magnetic field inside the solenoid directed to the right, the current at the top of the solenoid will be directed toward us along each loop, and at the bottom of the solenoid it'll be directed away from us along each loop. Now we can draw an Amperian loop to evaluate the line integral on the left of Ampere's law and the enclosed current on the right. The Amperian loop should look like this, coming straight down, along the loop in the direction of B, straight up, and then closing. I'll indicate this for the direction of the line integral and give the loop a length L. The only contribution to the line integral on the left of Ampere's law comes from the magnetic field inside the solenoid, so that gives us B times dl integrated along that leg. The two vertical legs give us no contribution because they're perpendicular to the magnetic field, and the orange leg outside of the solenoid gives us no contribution because the magnetic field there is approximately zero. So the integral of B times dl inside the solenoid is equal to mu naught times the enclosed current. The current enclosed by the orange loop is the number of turns that are enclosed. I'll call it n sub l, the number of turns in length L, times the current I. In the figure that I drew above, n sub l equals 3. It encloses 3 loops. So we can evaluate the integral on the left and solve for the magnetic field. It equals mu naught times the number of enclosed loops times the current I over the loop length L. And that simplifies to mu naught little n times I, which is the expression that we used above that we wanted to find.